this is what your investigation is going to look like. Okay, this is the file's on DMAP. I think I'll put it on there. If I haven't, I'll put it on there after I've done this. But the investigation that we're going to do this year is looking at two particular types of functions that are no longer required for the course. We used to actually have to know about these specifically. But what they do is allow us to do a whole heap of stuff with the calculus we already know. So effectively, you're just applying calculus stuff that you've already done to two particular types of models or functions that can be modeling for particular situations. So the investigation is made into three parts. The first part is looking at what is called a surge function. And the first part, everyone's going to get similar results, okay? Because realistically, you're just going through a set of steps. It's very led through. It tells you what you're trying to do. It's similar in a way to some of the investigations you've done in the past where you look at varying some of these constants and seeing what it does to the graph, okay? There's a conjecture that you need to make and then prove, all right? But effectively, it's led through, okay? It tells you the parts that you need to do, all right? But why? Well, that's because really the surge function isn't a requirement to know all that stuff for the course for the exam, but for the investigation, it's a good type of thing to do. Part two is going to be looking at the other type of function, which is called a logistic function. Okay, you can see there's less dot points. Effectively, what they're saying is that probably you should do similar sort of stuff to here as much as you can. But you're trying to find out, in part 1 and 2, you're trying to find out about surge and logistic functions and find out what sort of features they have and what changing the constants do. The final part is where you're going to get your marks, effectively. I mean, you obviously have to do part 1 and 2, and you have to complete that thoroughly to show, you know, the maths knowledge and all that sort of stuff. But part 3 is where you're going to get your high marks. That's how you get up into the A's. And that is where you decide to use either a surge or a logistic function, or perhaps both, depending on what your situation is. It is to model and investigate one of the following scenarios. Now, it says one of the following scenarios, but you'll notice the last one says a suitable alternative of your choosing. So realistically, any sort of scenario that you can come up with. But there are a list of things here that would be suitable to do. Okay, and you don't all have to pick different ones, obviously, but remembering that, you know, the actual scenario you come up with, if you've got, say, a crowd leaving a sports venue, we'll have a look at what that means in a minute, you would pick a different situation than other people. Don't all pick, you know, a Crows match or something like that to do. That doesn't mean probably a lot to people. What I want to show you first is just what a basic surge and logistic function look like. So this one here, this is a surge function. What you notice in terms of the graph, or if I sort of zoom out, you can see some of the features of the graph. It comes through here at the origin. It has this sort of lump, and if you consider just this space here, you'd almost call that like a skewed distribution, if you're thinking about distributions. But effectively, what happens is we get a rapid rise to a maximum, all right? And that maximum is a global maximum. It's the maximum point of the whole function, no matter what x value you have. But when it turns, it tapers back down much slower, okay? And it tends towards going back down to 0, okay? Yeah. You could consider perhaps projectile motion when you've got air resistance involved in it. Maybe. What features are things that you're going to be looking at? You're going to be looking at maximums. What's the slope at the maximum? Well, obviously the slope is 0. Somewhere in here, there must be an inflection point because it goes from concave down to concave up. There is an asymptote here. Okay. It's tending towards going to 0. It doesn't make it to 0. in a lot of surge functions that when we're modeling real data, we won't consider going below 0 because the whatever we're modeling doesn't make sense to go below 0. Okay, but the function itself will go below 0. So that's a general shape. It's got this sort of funny lump in it. The logistic function, oops, that's a bit zoomed out. Let's just zoom it out. Has this sort of general shape here. Okay, now it may, in this case here, it's not gone through 0, 0. You can see that. Perhaps that can change. Perhaps that can change in the surge function too. You need to look at it when you're investigating it. But your logistic function will have this sort of two asymptotes, and they link up by this very often quite steep section in here. All right, must have a inflection point in here somewhere. But you'll notice that it reaches, or it asymptotes towards a maximum. Okay, and obviously it starts down. In this case, it starts down in 0. All right, you're going to investigate what happens in some of those changes. Why those functions? You can notice that both these two functions do have e in them. Okay, so these are, this is an application of exponential functions. Okay, you will probably need, or you will need to use the natural log in some of your working to deal with that. Okay, so this really is an investigation that allows you to use the skills you've learnt so far up to this point. Okay, and sort of apply them. Why these functions? What's so special about them? Well, if we consider some of these situations and think about how do these things occur, or what happens in there. Let's think of a crowd leaving a sporting venue as an example. Okay, and if we were going to model that, so I've got two models there. I know they're a bit scale-wise not great. Two models there for a crowd leaving a sporting venue. You might have time going along the x-axis, okay, and perhaps the number of people that are, I don't know, the number of people still in the sporting venue or something like that. Okay. Hopefully, the logistic model, the red one, is not really great for modelling that. Okay, because what it's saying is, well, people are going into a sporting venue. All right. It might be that you're not actually doing the number of people in there. It might be the rate that they are going through the gates. Okay, and when, if you think about people leaving a game, then you'll get a real sort of rush very quickly. All right, you get the people that want to get going pretty quick. All right, and then it will slowly, then you get the people that hang around for a while and slowly sort of peter out. That model may not work all that well for that situation, because realistically there'd probably be a limit to how fast. There'd be a rate at which they can't be leaving any faster. You know what it's like when you've got gates and there's that many people trying to go through, so perhaps it should have had a flat spot in it. Another example, or perhaps an easier one to understand, would be people that are the sort of number of people that are entering, maybe. Although that's probably not as good either, because you are, you would imagine there is a peak number of people early, okay, but it shouldn't taper out like that if you're going to go and enter a place. Another example that's very useful for this is how medicines work. So if you think about something like a painkiller, when a painkiller is taken, if this was time, and this is like how effective, the effectiveness, some sort of number to the effectiveness of the painkiller, okay? And, it takes a bit of time to work, but at some point it reaches its peak pain-killing ability, but then it will taper off slowly, all right? So it works relatively quick, but then the effect sort of lingers and it slowly, leaves the body in that sort of fashion. What else we got there? So those that are doing chemistry, all right. There's the pH level in a titration. Okay, if you were to look at this function here for that, All right, when you have the pH level changing in a solution, pH is a log scale. Okay, so it's a to the power 10 sort of scale. When you get to around a neutral sort of pH, very small amounts of change or very small amounts of volume can make a big change in pH really quickly. But as the pH gets extreme, either up into the basic end or down in the acidic end, then it takes a lot more to change, and effectively it will taper off to a point where you can't change it any further, because that is really the concentration of the hydrogen ions that you're going to get no matter what when you keep adding the acid or the base. Depends which way you're going, that's right. Okay, so there are situations like that. So you can look at this: the limited growth of a population, the acceleration of a car, traffic density during peak hour, the spread of information in a group of people. So if you think about the spread of information in a group of people, then this would be a good model, because you'd hit a point where everyone knows, so you can't spread the information any further. Okay. I don't want to go into too much detail. I want you to, there's the internet's a massive source. You can go and look at all sorts of things. Okay. But when you come to actually doing your model, try and get or find some sort of realistic data. It doesn't mean you need to go out and measure stuff. It's not about going out and doing a whole heap of work, finding sort of raw data. But if you were going to do a sporting venue, then you can get some numbers or something. You can say, well, this is the maximum capacity for the stadium. Okay, you could look at making up some numbers that say, okay, well, the game starts at this time, the gates open at this time, so I've got some sort of values that I can plug in and vary a little bit. Okay, so what you're trying to do is come up with some sort of semi-realistic investigation into some sort of situation. That is the part where you get your marks, like I said. Now, because it's an investigation, I don't want to show you too much more, really. But what I am going to show you is an exemplar thing. But I'm going to do it fairly quickly, because the idea is that you don't, you need to do your own work with it as well. But at least you can see what a finished product might look like. This is not a high-end A, but it's also not a bad one either. All right? The reason that they haven't got probably, well, what I would mark it as not being really high marks, is they haven't really done enough in the part 3 section. That's too thin. The first two parts look okay. Okay? Let's just go back to the task sheet first before we go any further. So you've got 3 parts. It says select a suitable function to model your scenario in part 3. State the values of any constants that you're going to use and why you're using those constants. Or you might come up with and say, well, the constant's going to be within this range. Explain why you're going to say it's between this range or whatever. Obviously, have a sketch of your graph. When it says draw a sketch, well, use Desmos, GeoGebra or something. Don't talk by hand. Okay, look at the features of the graph, the reasonableness of the model, and the conclusions you make. Justify any decisions and limitations. What you'll notice is that in maths, it's all about pages, not about words, which is not great, and I really want you to consider that more words doesn't mean it's heaps better. Okay? So, 15 single-sided A4 pages, if you put your font down to, like size 10 and fairly narrow and all that sort of stuff, and make your margins wide, you can fill a hell of a lot of words in 15 pages. That's not the aim of this. Okay? It's certainly, you don't need to be doing, 5,000, 6,000 words. That's just ridiculous. It's not what it's about. Okay? So just, your pages, include your, doing some calculations, drawing your graphs in it, all that stuff as well. And you don't want to make them crammed up in time. Okay? What it says here, where did I say it? I thought I said it here somewhere. For this section, write your response as a report, which includes an introduction, a main body, and a conclusion. So your part 3 is sort of like a proper report style thing. That doesn't mean that you just answer questions in the first part. And the example does that quite well. I'll show you what it, and so that'll help you get an idea of how I would set that first part out. Okay, but the part 3 should be, your sort of investigation, which has its own little introduction about your, about your model that you're doing. So you can see here, this stuff here is really about part 3, an outline of the problem and context, the method required, so how you're going to go about it, showing your maths, apply the maths, okay, and analyze that sort of stuff. And so that should be that should be more than half of your pages. Doesn't mean that needs to be 9 pages, because you don't have to use 15, but it should be probably more than half. It's where you're going to get the higher marks. It's where you're showing your extended knowledge. You should be trying to extend yourself. And what do I mean by that? If we just look at this is an example to help with it. This example says repeated doses of a medicine. Okay, so what you might be looking at is investigating something like that, but where might it be that you have to take another dose? Panadol's every 4 hours or something. Okay, and if you took another dose, then at that point the function should start again. Almost. Like it should come back up, because you then sort of re-top up. So what does that do? And you can have a look at the model in that way and just extend things. Don't just go for the basics. You marked on all of the performance standards for this investigation. Okay, so comprehensive knowledge and understanding of the concepts and relationships. So that comes from part 1, 2, and 3, because you're showing, you're doing some stuff which is just mathematical and sort of making a conjecture and proving the conjecture and doing some stuff like that. And then you're going to apply that to your own model. So all parts there. Same here. Can you do the maths well? Effectively, can you use the sort of the correct steps to do things? Can you show whatever you need to show? The application of mathematical models, really this is part 3, because you're developing a model from data. Okay, and so that's why this one is predominantly from part 3. Okay, this part's for all of the bits. Can you use the electronic technology to draw your graphs, all that sort of stuff? Shouldn't be a problem to get marks there. You've got a conjecture. If you can, making some sort of conjecture in part 3 might be useful, but certainly you do that in part 1. You're asked to do it in part 1. But if you can find somewhere else to have a go at it, okay, then that's useful as well. Communication and notation, I would say that both those go hand in hand. All right. Importantly, when you're writing the whole lot, when you're writing, making sure you're using the right notation, the right language, and here you're actually backing up what you're saying, which goes with this one as well. Okay, so your conclusions should obviously be logical, but on top of that, your conclusion needs to talk about how reasonable is that result. Is that real life, or is there a problem with it for whatever reason? And are there limitations in your model? What factors would actually change what would happen in real life, and how much might they change it? And can you model that sort of stuff? Okay, and then the results. You can see I always find that this and this tend to go hand in hand. You're not going to separate them out. If you've interpreted the results in the context of the problem and said what the results are, then you're probably drawing logical conclusions at the same time. Okay, but they're the things you need to cover. You really should look at that and see, do I do those things? Okay, do I do a lot of that stuff, or am I really only down to I generally talk about the interpretation of the results, or do I do it thoroughly? Okay, so what is it going to look like? If we have a look here, this is just an example. So you can see this person has just gone straight into the first part and said the surge function. That is fine. They're not introducing this whole overall part, because we're not really asking for that to happen until you get to part 3. But don't put part 1. do what they've done and just say, okay, the surge function is the first thing we're looking at. There's a bit of information that they've found out. They had to change the value, which is what you have to do, so you can see that they get some different graphs. The graph is done quite well. It's labelled well. Okay, so labelling the important points, you can see here we've got the maximum or the stationary point, but then also an inflection point labelled. Okay, using colour to help is useful, but you can see we're changing the values of A when B is equal to 4 and seeing what happens. Okay, they've got a table of those points. Notice that in here, these points are given as decimal, but in here they're given in their exact form with E in it. All right, that is probably going to be something that's going to be useful. Some sort of information about it, not very well set out around the table there. I would like that set out better. Another thing also would be that you should have figure 1, blah, 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 blah. Okay, so make sure you label those sorts of things. All right, they've done then when they change the value of B, what happens? A bit better set out with the table, but once again, where's the headings and that sort of stuff for that? Okay. Notice that then they just use these subheadings. That's perfectly fine. It's exactly what I would do. Okay, so observation from when the value of B was changed, changing the value of B. This is just not set out very well. That should have been down. Observation from the surge graph when the value of A was changed. Blah blah blah. They've made a conjecture. Tried to prove it. Looks like they've proved it. Okay, and then they've gone into. If we look in here, comment on the suitability of the surge function in modelling medicinal doses by relating the features of the graph to the effect that a medicinal dose has on a body. Okay, so they've, significance of surge function in relation to medicine. All right, they've labelled some of the bits of the graph. They've talked about it, limitations in real life. So it's a little bit of information about that. Then they've gone straight into the logistic function. That's fine. Okay, same idea. Looked at the graphs, found the information they needed to, recorded the information. You can see there's natural log in it. Done the same thing, changing there. What's the observations? What's happened? Significance of that. So if we go down here, it says relate that to a limited growth model. Okay, so maximum growth rate, maximum number, and some informations. What's the limitations of real life contexts? Blah blah blah. They've talked about viruses growing and how their population would be, etc. Then they've gone into this. Now, what I would say is this is where you should be writing it as a report. Okay, I don't know what the concert was, but they've said it was at Adelaide Oval. They've talked about, 50,000 people can go there. They've come up with I'm going to use a logistic model. They're saying, how am I going to work out what the unknown values are? So they've done some working to say what they're going to be for value A and for B. Then they've put their model up. Okay. The observations of what's happening from that model, the limitations, and a conclusion. You can see that that's fairly thin. There's not a lot of stuff in that. Okay. I would say that would comfortably be a C, but to bump it up into the B's and A's, this is the part that needs a lot more in it. There's not much to it. It's very thin in there, and you can see that realistically that part is. I don't know where was I up to. Wrong spot. Don't know. It's not mine. So that's what, 1 page, 2 pages, and a little bit out of their sort of maximum 15. But they're actually, 11 pages long. So really only about 2 of them, 2 and a little bit of them, had that sort of own work stuff. That's what separates everybody out. Okay, so it's really important in the investigation that your first bit, it's going to be very similar. I mean, if we have a look at what it asks you to do, it says on the same set of axes, graph the function and the derivative. In fact, they didn't graph the derivative, so. In fact, they're on probably We might just pass through, but they haven't done that part. But for the case when A equals 10 and B equals 4, repeat the investigation for 3 different values of A while maintaining B equals 4. So everyone's going to have B equals 4, but you might have a bit of variety in what A's you use. Okay, so there's going to be a little bit of variety, but realistically, it's not going to be much. Okay, so if we go through a lot of that, everyone's going to get very similar stuff in that part 1 and part 2. That is why part 3 is so vital. Okay, that is the part that you really need to spend your time really sort of thinking about how you can investigate it and how you can extend that investigation and use bits and try different things. Compare it to what might be real and have a look at what the model says and say, okay, well, this part of the model looks nice, but if I go further in time, it starts to get a little bit shaky on really, I don't think that's how it would happen. These are probably some of the reasons or all that sort of stuff. Okay? So, yeah, don't probably perhaps use that exemplars part 3 as a good guide to how much you would need. All right, it should be at least probably 2/3 of your report. I couldn't show one last year because I didn't have one because they were new investigations. That's not from last year because we didn't do that one, but people have put them up so that we can use it. So what I hope it does is help you see the layout. More than anything, I think that's one of the things that's often scary with investigations is how to actually set these things out. Okay, and like I said, most of it is not bad. Their graphs are nice. They just could have some, title and caption to it. In this section here, this is fairly nice. Okay, set out pretty well. They've actually put some, therefore, blah, 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 substitute T into. They've written some stuff around it. Okay, you can see you don't need a hell of a lot of bits in it. So, the set out wise, it's actually pretty good. Okay, but what you need to look at is, okay, well, what content do I really need? You probably don't need any more content much in terms of space used for those first 2 parts. All right, because really, if you're covering what's there and you show it logically and you write about it, okay, then that's fine. That's what you need. Okay, if they had extended, they still had another 4 pages or nearly 5 pages, I think, because page 11 had very little on it. Plus, you've got pages like that. All right, they had plenty of room still to be able to expand out the part 3 stuff. Okay, but if we look at this as just a bit of a guide in terms of, it's a bit stupid how it does that, but graphs should try and be that big. All right, don't try and shove them down really small so you can get more words in, because you don't need that many more words. All right, that's plenty big enough, but I wouldn't go a lot smaller. Okay, obviously here you could have used that space, wouldn't have been a problem. All right. And, if you look at their font size, it's a reasonable font size. It's not tiny. It's not all crammed in. I'm not actually sure whether there are black and white things written. I'll have to have a look because I haven't got it written in a lot of places, but use common sense. Okay, it's not designed to be, it shouldn't be considered to be thousands and thousands of words. Last year's group, lots of them did too much. It was too much, and they spent too long on it. And if anything, yes, they got good marks for their investigation, but perhaps it was slightly detrimental to exam results in the end, because that would have been, if they'd used that time to be doing more practice of the questions, then that would have been useful. I mean, I can show you very quickly in there because they're not even the here. Tests. So if I look at this one for an example as an example of far, far, far too much.
It's not much.
All right. And there's a reason why I've taken this out, because realistically, you know, it's set out. It was nice. Look, in the end, good, thorough, over the top investigation. Well, you can see what I mean about font, and you can see what I mean about margins. All right. No, but what I'm saying is that this was not the only one. You can see that was not the only one that got really good marks, but it's far too much. It's far too much. 20%. Is that right? 20. Let me make sure. Yes, but you get a draft, so I can give you, like, I can do one full proper draft. Okay, so that's important to be aware of. Let me just 100% make sure that I'm right with that. We're still recording, so let's just stop that.